So we're going to just kind of do this is a kind of a review. It's on our last set of notes actually, and there are some things we can always count on. And those are the things that we're going to talk about up here at the top. When changing dimensions, it can be referred to as a scale factor. Just like we found the scale factor in the homework for today. The figures changed. The new one was either larger or it was smaller. Whatever that ratio of corresponding size was called the scale factor. So, when we're talking about volume today, we're going to say that if they ask you for the ratio of corresponding dimensions instead of sides, okay? They talk about dimensions instead of sides because they are three-dimensional figures, three-dimensional objects. So, really the same thing. Ratio of corresponding dimensions, ratio of corresponding sides, scale factor, they all mean the same thing. Okay, what did we decide? If the figure gets larger, the scale factor or the ratio of corresponding dimensions must be what?
Greater.
Must be greater than 1. If it gets larger, your scale factor better be greater than 1. If the figure gets smaller, the scale factor or ratio of corresponding dimensions must be smaller than 1. And again, I'm asking you, you can't learn this stuff without making your brain do some critical thinking. Don't just do the math problems to get the answers. Stop and say to yourself, does my answer make sense? If you ended up with a scale factor less than 1, but yet the new object is bigger, your brain should say, hey, wait a minute, there's a problem here. I can't stop here and just be satisfied with this. I need to say, my scale factor should have turned out to be greater than 1 because the object got bigger. Or vice versa. If it got smaller, then our scale factor better be less than 1. So take the time to process that. That's how you're going to learn it too, other than just doing those problems and saying and getting those answers. So again, when they're asking you for the ratio of volumes, just like we've talked about the ratio of perimeters, we've talked about the ratio of areas, now we're going to talk about the ratio of volumes. If they ask you for the ratio of volume, they're really just asking you how many times larger or smaller did the figure get. So what did we learn yesterday in our exploration when we were working with volumes? What happened? You were making cubes that were 1 by 1 by 1, and I made a cube that was 2 by 2 by 2. So in other words, our scale factor, what was the scale factor there? 1 by 1 by 1 was what you were making. I had 2 by 2 by 2. What was the scale factor? Just 2. My sides were 2 units long, actually inches, wasn't it? Mine were 2 inches long and yours was 1 inch long. 2 over 1 is 2. So the scale factor was 2. So did that mean then we talked about the volumes of them and stuff, so does that mean then that the volume of my cube was twice the volume of your cube? Is that what happened? Is that what we ended up with? Could you only get 2 of your cubes in my cube? How many were you able to get in there? Look on your sheet. 8. So the ratio of volumes was what? 8. Not 2. It was 8. Well, that isn't 2 times itself. Because what's 2 times itself? 4. So what did we decide yesterday then? The ratio of volumes, in other words, it didn't get just 2 times 2 bigger. It got 2 times 2 times 2 bigger. It got the scale factor times itself 3 times. Because 2 times 2 times 2 is 8. And I want you to start putting this together also. Volume means 3-dimensional. So if it's 3-dimensional, that means you're going to use the scale factor 3 times. Area is 2-dimensional. It's flat. It's 2-dimensional. And you take the scale factor times itself. You only use it twice. 2-dimensional, you use the scale factor twice. Perimeter. Perimeter is the distance around, so we could just take that and we could lay it all out in one big long string. That's only 1-dimensional. If it's only one-dimensional, you only use the scale factor once. So the ratio of perimeters is the scale factor. Stay with me. The ratio of the perimeters is the scale factor. The ratio of the areas is the scale factor times itself. And the ratio of the volumes is the scale factor times itself 3 times. Yeah. So that's just kind of like a summary of what we should have found through all of these explorations that we did. Okay, let's work with a three-dimensional object here. We have a prism A, and it says the dimensions were doubled to form prism B. We're going to answer these questions below. What are the dimensions of prism B? If the dimensions were doubled,
10, 12.
so this 5 inches would become 10 inches. And this 6 inches would become 12 inches. And this 3 inches would become 6 inches. So we're going to say it is a 10 inch by, we use little x's like this, by 12 inch by 6 inch. Those are its dimensions. It's a 10 by 12 by 6. The other one was a 5 by 6 by 3. Okay. Next question is, what's the ratio of corresponding dimensions?
So 10 over 5 over 6 and 6 over 3.
Yeah, so 10, the new one compared to the old. And that is equal to what? 2. Or we could compare, what's another comparison we could make? 12 over 6. And that is? 2. Or, we have one more comparison we can make. 6 over 3, and that is? 2. So what's the ratio of corresponding dimensions? 2. It's just 2. We got it every time, didn't we? We really only need it. They're similar figures. We should really only have to set it up once, but we just verified that it doesn't matter which set of dimensions you use, the length, the width, or the height. When you set up your ratio of corresponding dimensions, they should all turn out to be 2. What is that 2 in this problem? It's the scale factor, isn't it? We doubled the dimensions. That's the scale factor. Okay? What's the volume of prism A? How are we going to find that? Length times width times height. So we're going to take
90.
5 times 6 times 3. Which is 90. Okay. Anybody know what the label on that would be?
Inches squared.
Not squared. We have
Cubed.
a 3-dimensional. Yeah, inches cubed. Okay, what's the volume of prism B then? How are we going to get it? Calculator. Okay, well first we're going to show what we're going to put into our calculator. 10 times 12 times 6.
720.
720, okay. And the label on that would be? Inches cubed. Okay, and be really careful, people. Don't put that little cube behind the number and then write the word inches. Or the abbreviation inches. The cubed is, it's the inches that are cubed, not the number that's cubed. It's cubic inches. And cubic inches mean you made a cubic inch yesterday. That's what your little cube was. You had a cubic inch right there in your hands. So this is 720 of those. So what is the ratio of the volumes? How are you going to get that?
720 over 90.
720, the new volume over the old volume.
It's 80 divided by
720 divided by 90, sure?
90.
It's 8?
80.
It's 80.
No. It's 8. It's 8.
I'm thinking that, I don't, you know,
Eight.
I'm thinking I could say, well, these guys will cancel, and 72 divided by 9, oh, that's 8, right? Yeah. So the ratio of volumes is 8, and those aren't inches cubed, you guys remember, that's just a ratio of volumes. That is telling us what then?
It's 8 times bigger.
It's 8 times bigger. The new prism is 8 times bigger than the old one, the original one. So it says, how is the ratio of volumes related to the corresponding dimensions? Well, 8 is equal to what? What times itself 3 times 2. Remember our scale factor. Remember, this is ratio of corresponding dimensions. That's our 2, you guys, right there. We got that earlier. Up above, we said the ratio of corresponding dimensions is 2. It says, how is the ratio of volumes related? Well, the ratio of volumes is the scale factor times itself the ratio of corresponding dimensions, also known as the scale factor. So the ratio of volumes, we can say, how is it related to that ratio of corresponding dimensions? How is it related to the scale factor? It is the scale factor times itself. What do? Scale factor times itself 3 times. Three-dimensional volume. Scale factor times itself 3 times. Area. How many dimensions? 2-dimensional. The ratio of the areas is the scale factor times itself, not times 2, times itself. Yeah, it's only used twice. Ratio of the perimeters. Perimeter is 1-dimensional. So the ratio of the perimeters is the scale factor itself, just one scale factor. So the perimeter changes by the same amount that the sides change by. The area changes by the scale factor times itself. The volume changes by the scale factor times itself 3 times. Okay, so do you think we could have found the ratio of the volumes without finding the volume of each? What do you think? Did we really have to go through all that work finding that volume? Think there were any shortcuts? Yeah. From what we learned yesterday and from what we stated? What do you think we could have done instead? What if you're not very good at drawing 3-dimensional objects and you don't want to have to draw them? What are you going to do? Multiply the dimensions 3 times? Think that's going to work? So give me an example in this one how we would have gotten the ratio of volumes. What is the ratio of volumes again, you guys? What is it in this one? No, what's the ratio of volumes? What number is it in this one? 8. Well, I don't know. I get lots of mumbling going on. The ratio of volumes is 8. How could we have gotten that without actually going and finding all that volume? What could we have done, Emerson?
Couldn't you taken your part 2, you know how we put all over the fractions?
Yeah.
And then you know how we all got 2 for it?
Yeah.
And couldn't you just taken 2 times 2 times 2 times it's equal 8? Because obviously the answer is 8, and the volume of it you need to take it times 3 or 2 to find out what it's like. I don't know how to explain.
I know exactly what she's saying. She's saying, hey, wait a minute, you guys. We found out that the ratio of the corresponding sides, the scale factor was 2. And we also have just learned that the ratio of volumes is the scale factor times itself 3 times. So all you have to do is take the scale factor and cube it, multiply, use it 3 times, multiply with it 3 times. But did we even have to do the ratio of corresponding sides? Guess what? What does this word tell us right here?
That is multiplied by 2.
And what does that give us then? If it's multiplied by 2, what's the scale factor? 2. This actually right here tells us what the scale factor is, doesn't it?
Yeah.
Yeah. So in reality, we probably didn't have to even do all that. We could have just said, yes, the scale factor, you could go ahead and fill this in, the scale factor times itself 3 times is the ratio of volumes. In other words, it tells us how many times bigger or how many times smaller it got. That's what ratio of volumes means. How many times bigger did it get? In this case, it got bigger. How many times bigger did it get? No, we doubled the dimensions. 8 times bigger. The prism got 8 times bigger. It may not look like it on the picture. You can't go by the picture necessarily. But 8 of those smaller prisms should fit inside and fill up all the space in it. 8 of them should fit inside that bigger prism. Isn't that what we did yesterday? Didn't you find that 8 of your little cubes filled up my cube that was a 2 by 2 by 2? When I doubled the dimensions? What happened when we tripled them, you guys? Remember I made that bigger cube and I tripled it. Anybody remember how many cubes fit in then?
27.
27. Well, where would 27 come from?
3 times
3 times 3 times 3. The scale factor times itself 3 times. So in reality, we can sometimes save ourselves some work. We can count on this. So go back and count and use some, try to do stuff without drawing pictures. I'm not saying you can't draw pictures. Feel free. A cube has a side length of 4 inches. A scale factor of 2 is applied to the cubes. How many of the original cubes would fit inside the new cube? Well, I think the first thing you want to always do is you want to say, do I know the scale factor?
Yes.
What is our scale factor?
2.
2. We want to know fit inside. That kind of sounds to me like do we need the ratio of perimeters, or the ratio of areas,
Area.
or the ratio of volumes?
Area.
Fit inside? Not on top of. Fit inside. Yeah, we need the ratio of volumes. Fit inside. Let's write that down. Fit inside tells us we need the ratio of volumes. How many would fit inside? We need to know the ratio of volumes. How many times bigger did it get? And we know it's going to get bigger because what?
Scale factor is bigger.
Scale factor is bigger than 1. So we know it's going to get bigger. So, do we know how to find the ratio of volumes if we know the scale factor?
Yes.
What is it? How do we find it without drawing the picture and finding those volumes and going through all that work? What could we do? Scale factor times itself
3 times.
3 times. Volume 3 times. So we need the ratio of volumes. We're going to take the 2 times the 2 times the 2. And what do we get? 8. So the question was, how many of the original cubes would fit inside the new cube? 8 cubes. 8 original cubes we will put. We're going to talk about which ones we're talking about. 8 original cubes fit inside the new cube. And in reality, when we start a sentence, if it starts with a number, we should actually write it in words. 8 original cubes fit inside the new cube. So notice it doesn't matter that it started with a bigger cube, 4 by 4 by 4. After we double the size, and now we have an 8 by 8 by 8. 8 of those 4 by 4 by 4s would fit in that 8 by 8 by 8. Just like yesterday, 8 of the 1 by 1 by 1s fit in the 2 by 2 by 2. No matter how big it is to start with, if you double the size of the dimensions, that's what's going to happen. You'll get 8, it'll get 8 times bigger. Any questions about that? Trey?
I did it a different way, but I have the same answer.
Okay, what'd you do?
What I did, I took 4 times 2 and I got 8, and I multiplied 8 3 times. I got 512.
So you found the volume of the new one.
4 times 4 is 64.
Yeah, that's another way to do it. You found the volume of the new one, which is 512, did you say? Okay, and the volume of the old one, which is 64. New over old, 512 over 64, divide it out, you get 8. That's another way to do it. Good job. Anybody else? Questions? Okay, so here we're taking the kind of like maybe what I call a shortcut. You might not consider it a shortcut. Something else might make more sense to you. Do the one that makes more sense to you. Okay, a cylinder. Can you give me an example of a cylinder in everyday life, Trey?
Pringles can.
Pringles can.
Soup
Yeah.
can.
Soup can. So we have a cylinder. It has a radius of 8 centimeters and a height of 14 centimeters. Each dimension of the cylinder is multiplied by 1/2 to form a new cylinder. Is the new cylinder going to be bigger or smaller?
Smaller. Smaller.
Better get smaller because the scale factor is less than 1. Okay. How are the ratio of volumes compared to the ratio of the corresponding dimensions? Remember, what does this mean? What's this the same as? Scale factor. That's the same as the scale factor. Question is, do we know the scale factor?
No. Yes.
Anybody think? Okay, I got a no and I got a yes. Okay, the yes person, what's our scale factor? 1/2. It says it right here. Multiplied by 1/2. There's our scale factor. It's 1/2. Does that mean then that the new cylinder is going to be half as big? Would that new one is only going to be half as big, so only 2 of it would fit back in the original one? Okay, well they're asking about the ratio of volume, so that's what they're asking. What's going to happen to the size of it? Ratio of volumes. What's the shortcut we can take? I bet there aren't too many of you in here right now that are feeling real confident about finding the volume of a cylinder, are you? Anybody happen to know how to do that? Pi r squared h. So, yeah. Do we have enough information to do it? We do, but actually I'm thinking that's just way too much work because I got a lot easier way to do it. How about you? What can we do here?
8 times 1/2 is 14.
I don't want to make a new cylinder because I don't want to find the volume of either of them. It's too much work. I want to take a shortcut. Rose? Absolutely. You do 1/2 times 1/2 times 1/2. The scale factor times itself 3 times. That sure seems a lot easier than finding the new cylinder's dimensions and then finding the volume of both and then setting up a ratio because do we know how to multiply fractions? Yes, we do. Across the top, 1 times 1 times 1. 1. Across the bottom, 2 times 2 times 2. 8. So the ratio of volumes is 1/8. What does that tell us? And the new cylinder is 1/8 the size of the original one. Yeah, 1/8 the size of the original one. It got a little bit smaller, didn't it? It didn't get half as big. It's 1/8 as big. And if you can't, that doesn't make sense to you, just think of, something like a pizza cut into 8 pieces, and you only get one of them, versus half of it. You don't get quite as much when you get an eighth of a pizza versus a half, do you? So the new cylinder is 1/8 the size of the original one. So it doesn't just get half as big, it's only 1/8 as big. Thanks, Rose, for saving us a lot of work. Okay, let's move on to our last one. A cone has a volume of 36 pi centimeters cubed, and every dimension is multiplied by a scale factor to form a new cone. The new cone has a volume of 972 pi centimeters cubed. Is the new cone bigger or smaller? Bigger. That means the scale factor we get better be bigger than 1. Yeah, better be larger than 1 because they want us to find the scale factor. Well, do you remember how do we find the scale factor? Well, first of all, let's talk about setting up a ratio of volumes. So let's find the ratio of volumes first, because there's something we know that we can do after that. What goes upstairs, new or old?
New.
The new. So 972 pi goes upstairs, the new. And what goes downstairs? The old, which is 36 pi. Don't worry about those pi's in there, because there's one upstairs and there's one downstairs, and there's multiplication going on upstairs and there's multiplication going on downstairs. So what do you think we can do with those pi's?
Cancel them out.
They can cancel out. We can be like, see ya. And now we can divide 972 by 36.
$27.
27. So we just found the ratio of volume.
Scale factor.
Is that our scale factor?
No.
What do you think? Is that our scale factor? No. No, what do we have to do? Remember, the ratio of volumes is the same as, this is the same as the scale factor, let's just call it SF for now, scale factor times the scale factor times the scale factor. Isn't that what we do?
Yes.
Scale factor times itself 3 times is the ratio of volumes.
It's 19,600.
Oh, no, careful. The ratio of volumes, that means we have to get 27 has to become something times itself 3 times.
7.
9 times 9 times 9 is 27?
27 divided by
3 times 3 times 3.
13.5.
Oh, no. What times itself? Gotta have the same number. We just did this yesterday. I made one that was a 3 by 3 by 3, and you told me that 27 cubes fit in it when the scale factor was 3. 27 was, it was 27 times bigger. So the scale factor is 3. Not 27. The dimensions were then what? What did they do to the dimensions? They multiplied by 3. They tripled the dimensions, and the cylinder got, or the cone, excuse me, got how many times bigger?
3 times.
No.
27.
It got 27 times bigger. 3 was the scale factor. It got 27 times bigger.